The New Quantum Era,
a podcast
by Sebastian
and Kevin Roney.
Welcome to our podcast, The New Quantum Era. Hi, my name is Kevin Roney, and I'm here today with
Sebastian Hassinger.
Hey, and so we're both very interested in this area of quantum computing. We've scheduled a whole set of I think some pretty interesting interviews. This is our inaugural podcast, an interview with a physicist at the IBM Quantum Computing Division. We're both of us into the domain here of quantum computing because there's just so many interesting things on brand new computing models with huge amounts of potential, some really fascinating and deep science questions, and just some very, I think, beautiful, eloquent mathematics as well beneath it. So we're just trying to explore these topics because we find them really, really deep and really a deep draw to our interests. Hope it appeals to you as well.
Yeah. So what Kevin and I want to do with this podcast is we're going to feature an interview in each episode with people who are actively driving the domain forward. They may be scientists, researchers, industrial, academic background, what have you. They may be pioneers or on the cutting edge of what's happening today. And in each instance, we'll try to explore a variety of topics that they're passionate about, they're motivated by, and they have deep expertise in. Neither of us are quantum physicists, as we expect is true about most of our audience. And we're really looking at this field through our own individual backgrounds and lenses. As Kevin said, we find this fascinating, baffling, and exciting in equal measure. And we're hoping through these conversations to learn more ourselves and hopefully shed more light on the field for our listeners as well.
And so, look, if you're listening to this podcast, we're trying to appeal to people who are like us into, big science, new developments in technology, venture capital, issues around a bunch of topics. Mathematics and computability. There's just a very rich and appealing, swath of topics that are covered here. So hopefully that describes you. Hopefully you're still with us. I guess it's our hope that during these discussions and interviews on this topic, we're going to get into some depth, some substance. He's right. Neither of us are quantum physicists, but we're taking on, some pretty, ambitious interviews with people who are experts in the field. And we're not sticking at the surface with analogies and overall general descriptions of what quantum computing could be. We're trying to get into the nitty gritty. We're trying to see and grapple really with both the optimism and possibility of this field, but also, I think, many of the needed forms of sober skepticism concerning any development in new technology, because there's always the hype.
Right. Yeah. And I think this first interview with Nick Bronn from IBM Research is a really excellent introduction to the territory and the style of content you'll expect from this podcast. We cover a number of topics with Nick. He's obviously very passionate about the subject. And we dive into some foundational concepts like DiVincenzo's 5 criteria of quantum computing, which sort of laid a lot of the foundation for understanding what these systems needed to look like, what the engineering needed to be, and what the science that they needed to support, as well as sort of cutting edge developments and speculative, thoughts about where we might go with things as exotic as Majorana fermions and other concepts as well.
Yeah, the science experiments you can do on a quantum computer in very deep ways, it's kind of compelling. Another big draw for us. But I think another fantastic element, right, of this interview with Nick was just that we were able to get into deep detail on the specific nature of the function of transmons. As you know, if you're listening to this podcast, you probably know already, transmons are the leading contender for the key quantum computing architecture that have a lot of potential to produce at some point in our future, after a lot of other engineering challenges, commercially significant quantum volume. So knowing in some more detail besides, vague generalities is something we're trying to get to on this podcast. And we've gotten into, I think, some substance on transmons. That was fun for me. I had a couple of misconceptions he helped clear up for me, so that was really
as
useful.
Probably we all do, and that's a really good point, Kevin. I think one thing that I'd like to do, and we plan on doing, is having people with backgrounds in different aspects of the technology. As you said, there's transmon or superconducting qubits are one of the types of qubits that are being produced. There are trapped ions in IonQ and quantinuum systems, among others. There's now photonic qubits in development. There are neutral atom qubits in development. There's quantum dots. There's probably, I think the last time I checked the Wikipedia page, there are about 24 different quantum phenomena that might support computation in one form or another.
And then a whole zoo of measurement devices as well, right?
That's right. I mean, I came to this field about coming on 4 years ago now. And as a newcomer to the domain, I just found it incredibly confusing, all of the various moving parts. As you said, there's sort of a zoo at every level, at the hardware level, at the low level control software level. Things like error correction are extremely active areas of research where a lot of work still needs to be done. And then at the algorithm and application level, there's an enormous amount of speculation and curious exploration, and sometimes hyperbolic claims. And that's what we're going to be digging into, is trying to find our way through that landscape and make sense of what are the critical sort of challenges that face the field. What are some of the more enticing technologies that seem to be advancing our progress towards some kind of quantum advantage, and when and if we get to that quantum advantage, what is that going to look like? What are these things going to be good for? What are we going to learn in scientific terms, and what kind of value are we going to unlock in commercial terms?
Yeah, we're just doing our level best too within this fascinating domain, just if we can peer a little bit farther over the horizon.
So today we're going to be talking with Nick Bronn. And Nick, why don't you start with just a quick introduction of yourself and your background?
All right. Well, my name's Nick Bronn. I've been a research staff member at IBM Quantum for almost 8 years now, or just past 8 years. I started as a postdoc for 2 years and research staff member for 6 years, always in IBM Quantum. I came from a experimental condensed matter physics background. I think we might touch on some of that later today. Experimental condensed matter physics PhD from the University of Illinois. Currently, I've actually moved quite out of the lab and into the software scene using Qiskit, which is the IBM-supported open source framework for quantum computing, where I deal with kind of where the software meets the hardware, things such as pulse-level microwave control, quantum simulations, and the transpiler, which is the whole mass of how do you take an abstract circuit and turn it into something that can more or less run on a piece of quantum hardware.
So at what point in your academic career do you think you sort of were attracted to quantum computing rather than the condensed matter physics and started to get drawn into the field?
Great question. I was always interested in quantum computing, but in my university, the quantum computing groups were based on optical quantum computing. So my roommate, for example, studied under Paul Kriot, who was very well known for experimentally demonstrating a lot of the weird quantum paradoxes using photons. And there was very little, even in condensed matter, even in a university where superconductors were prevalent, about using superconducting qubits for quantum computing. And so it seemed to me that the field of condensed matter just hadn't caught up to it yet. Although there was a lot of excitement about the progress could be made, I did not realize at that point that there were opportunities. So when I applied to IBM, I applied for the most generic experimental postdoc and condensed matter, you possibly could have seen, do you know RF? Do you know electronic measurements? Do you know fabrication? Do you know low temperature physics? Do you know lasers, et cetera, et cetera? And I was like, well, I know most of those. And I figured it was actually going to be with the group that did graphene and nanotubes, which Phaedon Avoris used to lead. And I just assumed that that's who picked me up. But it turned out it was the quantum computing group that wanted to interview me. And I was like, oh, well, that sounds interesting. I'm really interested in that. I had no idea it's come this far. So wonderful. Let's give this a shot. But of course, one of the funny things about studying what I studied was I decided I really like condensed matter physics because it involves all the kind of branches of physics: statistical physics, electromagnetism, and quantum. Not really, it doesn't really involve classical mechanics or gravity or anything like that, but the other kind of big three. And then it's kind of all the technology that existed classically can be explained with device physics, and that's all based on these kind of solid state. It was called solid state physics, now condensed matter physics. That exists to explain all these things and make all this technological progress. And I thought, well, this is really interesting. I'm at this time where Moore's law is going to end or starts coming to an end. And so I should position myself as a physicist who understands these kinds of problems. And so I actually studied more like nanotechnology, graphene nanotubes, some things related to spintronics, which was another option I was looking into as well. And then it turns out quantum computing had gotten this far. So I completely switched gears and moved from classical computing and trying to use new kinds of technologies there to quantum computing, just an entirely different thing. But the use of superconductors was something I was familiar with, the use of the dilution refrigerators that you know and love and see and all the shiny things going on. I was used to that. The microwave measurement was a little different. I used to do low frequency measurement, but you can learn these things on the job. And so in the end, I ended up succeeding in a nonlinear way. I studied like nanoelectronics, but I ended up in quantum. And so I don't care. That worked out very well for me.
Yeah.
Such a great story. I mean, sometimes people's the arc of their career, it hits like a little moment of luck where they're fully prepared to ride the wave. But man, it just opened up for you, didn't it? It's a really interesting future for you.
That's right, Kevin. It really did open up for me. And to even think about when I started in 2013, the quantum group was about 25 people. We all ate lunch together every day at noon. We all sat at the same table.
And how big is the team now?
I can't talk about how big the team is now, of course. But
it's not 25 people.
I don't think I'm going to get censured if I say it's more than 25 people.
Okay, all right.
So, well, I'm just curious, at that point when you joined, did they have a functioning superconducting qubit? Was there a transmon that was operational at that point, or was it still building the first one in IBM?
Yeah, that's a great question. So the building of the transmons had happened at that point. We had probably not converged on the transmon that would we're never converging. We're always experimenting if you've looked at the scientific literature we've put out.
Yeah.
But at that time, we were essentially looking at coupling a small number of qubits together. A lot of these ideas were based on work that Jerry Chow did in graduate school and then brought to IBM. At that point, when I started, I think the biggest device was 3 qubits. And maybe in my first couple years, we had a really big demonstration on 4. So,
boy, huge breakthrough.
Yeah, huge breakthroughs.
So not that long before IBM put the first 5 qubit machine on the web, right? I mean, that would have been just a year or two afterwards, I think.
Exactly. That was 2016.
16.
And at that time, the biggest qubit processors were 7 and 8 qubits.
Right. It's funny, it seems like all of the explorations of technology of styles of qubits in the early 2000s all were sort of hitting that 3, 4, 5 kind of qubit range and then stalling out. And it really is extraordinary how there was kind of a moment at IBM in particular that sort of broke through that ceiling and started to really scale up. I mean, the announcement this week of the 127 qubit chip is kind of extraordinary when you think that 5 years ago it was 5.
Exactly. So when I started, we were using only commercial off-the-shelf microwave equipment. So putting together my own experiments with either 1 qubit or 2 qubits, like 1 qubit was a rack of electronics. 2 2 qubits was 2.5 racks of electronics or so because you needed extra for the 2 qubit interactions, for example.
Right.
So learning all the tricks and trials and tribulations of figuring out how to most efficiently use these signals, how to build your own electronics so that you can start scaling down in price and volume, essentially,
Right.
allows you to do a lot of work. And so one of the things I always try to say is the amount of work in classical electronics to control the quantum computer has been, also astronomical in this field to allow us to control 127 qubits. To make it relatively easy to go up, the classical electronics have to get more and more sophisticated. And so we've had, generations and generations of our custom-built, FPGA-based electronics that are then able to allow us to scale to this level. And that research isn't going to go away either because we need to continue that.
Yeah, it is really like you can't look anywhere in the field of quantum computing and not find significant challenges to the science and the engineering just to make it all work better.
Exactly.
We try as much as we can to pay with some care to the specific details of the science and the underlying mathematics, without going over the top and losing the audience. So we're doing our very best to appeal to people who are into deep tech. Maybe they're mathematical hobbyists. Maybe they're not. But they don't really have a lot of prior training in physics. But for that audience, which we feel like we're part of that and want to speak to that audience. I mean, I was hoping we could find a little bit of dialogue, a little back and forth on how a transmon does its thing. Because, there's a lot of stuff you could just read out there.
Right.
But, I mean, even in my own, I feel like I take the subject very seriously. I've been through many generations of understanding what I thought it was that are completely wrong. So it feels like many, amateurs who are not, from your point of view, are still catching up with even the basics as to how that thing does what it does. So would you mind delving in for a little while, a back and forth on the explanation?
Sure thing. I'd be happy to. The transmon qubit is a superconducting qubit that behaves like an oscillator. On oscillations of charge, which are the Cooper pairs, the way electrons pair up in superconductors, tunneling, quantum mechanically tunneling across something called a Josephson junction. And that Josephson junction is very important. So you have in a qubit maybe tens of Cooper pairs oscillating back and forth. You can do some calculations to figure out how many Cooper pairs are partaking in this dance and how and what the frequency of oscillation is. But basically, it's an oscillator. It's almost just like an LC circuit that you know from your circuits class in college. The difference is this Josephson junction is a very special element whereby the inductance of it depends on the current going through it, which means if you're oscillating faster, then the inductance through it is greater than, if I'm going the right direction, greater than the inductance if you're at the lowest frequency of oscillation.
That's a really interesting point. I mean, if I may interrupt, because what I've seen from a bunch of the background reading I've done is people are pointing very directly at the nonlinearity of the inductance as a key feature of this architecture. Did I have that right?
That's absolutely right. The nonlinearity is key for this kind of qubit because you can essentially, when you have a nonlinear oscillator, you get what we call an anharmonic oscillator. And that means that the energy level difference between your 0 and 1 level is different from your 1 and 2 level, which means it's addressable. It means you have a unique frequency between your 0 and 1 state that does not exist anywhere else inside of your transmon.
Now that point's finally clear. It's beginning to make sense to me.
So there are other schemes that take microwave oscillators and encode things such as cat states, which are an indefinite number of photons arranged in something called a coherent state. Where the kind of basis is not the number of photons, it's a superposition of a number of photons in this certain coherent superposition.
Perfect.
That's harder.
That's hard.
And so I want you to continue your flow, and I've got some more follow-up questions later when we get a little deeper.
Yeah. So there are people pursuing both ways of encoding. Sometimes you encode the quantum information in a linear oscillator, but then you need some nonlinearity to read it out. So almost always, like transmons are either used to help generate that nonlinearity or to store the information in a qubit.
Right, and that's sort of one of the fundamental attributes of any scheme to design a qubit is there has to be that the addressable energy level to create a two level system, right? So to actually support computation.
Right. So the DiVincenzo criteria is where I always like to begin when I discuss different kinds of quantum hardware.
Oh, wait, and it's spell that out for us.
The DiVincenzo criterion. Let's see if I could do this on the fly.
Quiz time. Sorry, dude.
You have to have an addressable qubit that you can control between a two-level system. You have to be able to initialize it in a fiducial state, which means you kind of like start in zero. That's easy to do because the qubits naturally decay pretty quickly. But there's always tricks you can do for other kinds of systems. You want to have a good measurement technique so that you can read out the state of the qubits at the end of the algorithm.
Is it the set of gates? Does he stipulate a universal set of gates?
You need a universal set of gates. Thanks for coming in there. It's been a long week. Which actually wasn't really known that you could do it this way in the early days of quantum computing, because we use in superconducting qubits we use 2-qubit gates and single qubit gates, and we don't have any higher order level of gates. But it turns out you can break down any arbitrary like n-qubit operation into these things. You can actually compile or even transpile, you might say, into the native gates that your hardware can actually use.
Right.
As a tensor product of these more simple operations.
Exactly. Yeah. So you're doing like tensoring and compositions of essentially, but everything breaks down. Yeah.
As you said, that would be work that happens in the transpiler then potentially. Like you'd write a complex circuit with assuming a universal set of gates, and then the transpiler would break that down into as you said, the native gates to be applied on the hardware.
So, for example, the Tafali was one of the first qubit gates that I think the Tafali was one of the first qubit operations that was first thought to be universal, and that's a 3-qubit operation. But for us, what happens is we would break that down into about 8 C-naughts and some single qubit rotations. You can implement it on a 3-qubit superconducting system as well.
Right. Which, of course, means that coherence times and error rates become more and more important the more complex the circuit is that you're trying to decompose into those. As you said, if you go from 1 Tafali goes to 8 C-naughts and a few others, and then you can very quickly see how that would become extremely complex in terms of the operation, and you'd need long coherence times and low error rates to actually carry it out, right?
Yes, that's exactly right. Speaking of complexity, when we were talking about transmons, people say, well, the transmon's such a simple qubit. It's just an n-harmonic oscillator. Like, yeah, well, of course. It's all super easy until you take 2 transmons and put them together. and then you get a rich behavior, which lots of physics and a lot of things going on, and it's very complicated. And you have to have, a bunch of theorists and computational physicists to help you figure out what you're doing.
Because I gather it's not just a problem of getting them to communicate well, but also preventing their unintended communication. Right? There's all sorts of interference that causes mayhem if you don't tackle it.
Absolutely, that's something we call crosstalk and spectator qubits, and that's actually why IBM has moved to this heavy hexagonal lattice where there's slightly less connectivity than a surface code. So if you have the square lattice, every qubit has 4 nearest neighbors. And in the heavy hex, it's like a qubit at every vertex of a hexagon and then an extra one between every vertex, which is what makes it heavy. And so every qubit is connected to 2 or 3 other qubits.
This is such great detail, Nick. I'm trying to ask a clarifying question that is my own personal analogy on how this stuff works. And if I've got this wrong, please fill me in. But it feels like you're pointing at the similarity with transmons and LC circuits. LC circuits from classical, this wave of electrons moving back and forth between the capacitor and through the inductor, right, from different sides of the capacitor. It's an oscillating wave of these swarms of electrons, right? And so that kind of like observation was really helpful, at least for me, in clarifying that, at least in the case of transmons, all the way down at that super cool temperature with the superconductivity active. Now the electrons, because this is the way it happens with superconductors, they're pairing up, and then there's tens of these Cooper pairs coming back and forth in sort of this oscillating wave. But if I'm not mistaken, and again, tell me if I'm wrong, I'm trying to catch up with this stuff. There's actually 2 sets of these Cooper pairs oscillating on 2 separate islands, so to speak, that are connected, right, via this junction that is essentially an insulating barrier, but there's a quantum effect of somehow them tunneling, so to speak, over back and forth. So there's 2 oscillating waves on either side of this junction that are essentially at the same frequency, the same magnitude. They might be out of phase, and that is the expression, if I'm not mistaken, of the quantum state of the systems. Do I have that right?
So that's close. That's actually a little closer to a different kind of qubit, because you can kind of build whatever wave function you want. See, the funny thing about this kind of, or thinking about these kinds of things is understanding, how do electrons pair up? You think about a wave function, you think about a macroscopic phase on a superconductor, and you can relate these to the actual motion and the wave function of the essentially electrons in a potential. You get different wave functions, and you kind of just label one to be 0 and label the other one to be 1, and these are your states. And as long as you can kind of address them well and add a photon and move from one to the other, then these kinds of things are allowed. So in the particular wave function of what it looks like in a transmon, it's more or less like how many in kind of a confined barrier, it's how many times the wave function crosses 0. So the first one doesn't cross 0 at all, and you have more of the wave function at the center, and then the first one, the wave function would have one node in it, which means it would cross 0. It would be antisymmetric, and that means the electrons would be more concentrated away from the center slightly.
I'm sorry. Basic question. What is 0 in this case? What is crossing 0?
Oh, sorry. The wave function crossing the 0. So the wave function represents the density or the probability amplitude of the density amplitude. I don't know if that's a thing. The probability amplitude of your electron being somewhere. And when it's negative, you can't have that with a probability, but you can have that with a probability amplitude. So the probability amplitude would go negative from positive, but your density would be the square of that, or the complex square of that.
Yes,
and so you have a real density. Right. And so this is actually, something like examples from chemistry where you have bonding and anti-bonding, and one has electrons close, the other one has electrons far away. So everything's kind of related in some way.
This is so helpful. Thank you. I'm just still searching for my own information, like at least some decent animation, right, of the ebb and flow of the electrons within a transmon. I spent a lot of time looking for such a thing. Haven't found it yet. So still searching.
I can show you. I can show you the wave functions of the transmon. I don't know if that will really help you, because we don't even think about the wave functions of the transmon. We think about we can create the state that is superpositions of these wave functions, and we just label them 0 and 1.
Yeah. And I have a taste for that kind of math, but I think our audience would perhaps maybe need something a little bit more concrete. So that's why I'm searching for animation.
Different frequencies of oscillation. That's all it is.
Okay. All right. Thank you. That helps a lot.
Yeah, no problem.
So I'm curious, Nick, like you mentioned sort of transitioning from experimental to more, the theory and the software. What sort of drove that? What was the motivator for you to sort of get more involved in programming these things, or thinking about how to program these things?
Well, if you haven't noticed, I really like talking about this stuff. So for a few years, I had kind of, been happy to go to quantum meetups, to conferences and seminars, and give talks on quantum in general, or what IBM's doing in quantum, or some aspect of quantum I find interesting. And that kind of getting out of the lab and enthusiasm for telling people about the hardware that exists in the lab that I'm very familiar with was kind of like there was an interest for someone with that kind of hardware knowledge, like someone who really knows their way around the lab, to be more public facing and interact with people who want to know exactly the questions you're asking me. How does this stuff actually work? And so having all that experience, and I've worked in a lot of different parts of IBM and a lot of different, mostly hardware things until then, gives me that kind of experience. And then looking at Qiskit and seeing what you can do with software development is kind of the practice. Well, I want to see, what am I going to do with a quantum computer when I'm on the other side of it? And I kind of take that same experimental framework. Well, what can I do? And I have a scratch directory. I just start programming things. I'm going to make a mixed state. I'm going to make, what was I just doing? I was looking at some error correction thing. I'm trying to make a video on that. I'm going to initialize an arbitrary state and see how well I can figure out how to do that, just using the tools in Qiskit, for example.
Right. So at this stage, I mean, it's a huge advantage then intimately knowing how the hardware behaves in approaching, writing something in code. Like you're intrinsically dependent on what's happening at the metal, basically. It's not like classical computing where you can sort of forget about what you're running on completely, right?
That's exactly right. And I know we're supposed to think about quantum computers as being a digital type thing. You have these fundamental universal gate set that is not necessarily a continuous thing. But if you understand how the physics of these microwave operations work, then sometimes you can frame certain problems in a more efficient way and reduce the overall amount of error that you incur. And that was, I guess, the biggest success I had coming out of the lab is I came across a research group in academia that wanted to do some quantum simulation. And
this is David Pecker, right?
This is David Pecker at University of Pittsburgh. Yes. And him and his postdoc, John Stenger, show me, this is the algorithm we're trying to do. And they said, well, it's only giving noise. And I said, well, of course it's only giving noise. You have 96 C naughts in there. That's way too much for qubits that have 1% error rate on C naught. And you can do this just by typing in 0.99 on your calculator to the 100th power and seeing that it's below 50% fidelity. That's a sanity check that you will not be able to get what you want out.
It's the definition of garbage.
Exactly. But because these were quantum simulation circuits, they had a certain structure to them that was essentially building these interactions out of the pairs of qubits. And by looking at that, I said, well, fundamentally, I know what the interaction of the C naught is at base. It's something called a ZX interaction that comes from echoed cross resonance, which is a very technical term for the way that IBM does 2-qubit interactions. And I said, well, I can take this 2-qubit interaction, I can build any of these other 2-qubit interactions out of it. And what that means is I only need to do the amount of entanglement that's necessary by the algorithm and not decompose it further into how you would do it if you only had access to C naughts and single qubit gates, thereby saving more than 50% in the timing of the algorithm.
And you were even shaping the pulses, I think, to try to get optimal performance out, right?
Right. We were actually just scaling them, and we were scaling them in a way, essentially the area under the curve is the amount of rotation you're doing, but you want to scale them in a certain way because you don't want to make things go bad, in a way. So you can scale that amount of area, but you don't want to, say, increase the amplitude, for example, because of the way these are calibrated. You can cause leakage if you increase the amplitude too much. Which you probably would if you tried to do that to a 2-qubit gate. And all of this, these pulse scaling techniques, they're very popular now. Now, we have at least 2 or 3 more papers, at least on the arXiv right now, that's been utilizing this technique. And it's in Qiskit now, so you don't even have to know how to scale pulses yourself. It's already available. You don't even need to know what a pulse is to use this technique.
That's such a great example of that intimate experimentalist knowledge informing an approach in the software that ends up being an abstraction that helps everybody without that having that kind of level of knowledge, right?
It's a fascinating thread too, Nick, because it could be that I'm a Qiskit hobbyist. There are numerous listeners, I'm sure, who are in the same camp. How would you recommend somebody who has not done a few decades in the lab doing that kind of work to acquire that intuition on what kind of factors, what kind of budget they should have for certain resources to know to avoid one idiom of code versus another? Because you do need to. It sounds like you do need to acknowledge the fact of the underlying architecture, or you're sunk.
Right. Well, as someone who really enjoys the details of the underlying architecture, I'm going to go ahead and say yes. Of course, you need to, at this point, understand what's going on in the architecture. Although, in the future, it's envisioned that you will not have to do that. In the meantime, I kind of, make my hay by taking what I know about the hardware and converting it into being able to do algorithms better. And I think these kinds of things will continue to be used. And so in the near term, these can be very important. In order to kind of look at best practices, this is something that's very interesting because we do have a large community of quantum computing users, and it's moving so fast that it's not very easy to kind of convey what the best way to do everything is. And this is a kind of a bottleneck that we've reached. Like, do we have a Slack channel? Do we have an email list? Like, we have all these documentations online. We have a lot of ways you can get to it, but there's no kind of standard operating procedure, no kind of best practices. And these are the things that I think we're going to, or I'm going to be helping to create to try and get to our, to get to our potential users, because nominally where I'm involved now is trying to get mainly academic, but it kind of goes for everyone, people using Qiskit for their own research purposes. So we have this tool. If I can show you how great this tool is, then you will pick it up. Because physicists are inherently lazy. If I can give them something that will make them lazier, they will take it. And they will use it.
I think you could substitute in humans instead of physicists there, but
I know humans is true, but we always have this talk that it's the physicists that are always thinking the hardest about how lazy can I be.
that's true. It's also a programmer mindset too.
I think that the mathematicians brag the same way. They
Yeah.
do the same thing. We're also super lazy, so we want to find a shortcut, right? So we might even be lazier than the physicists. I don't know, right?
I've never felt more like a programmer than when I spent an inordinate amount of time to avoid having to do something ever again. Like spending hours building a script to automate something I just never want to do again.
Exactly. So I think every kind of field has their own kind of version of this.
Yeah.
Probably true. Yeah.
I wonder if there's a way to encourage people to include like a Jupyter Notebook with their code in the papers they post to the archive. I would love to see more like running code that supports the work in a paper.
Absolutely. That's something we know that is a really good idea. There's been a lot of open science kind of initiatives and the like. So for example, the code I have for the Majorana braiding, it's available. I mean, you can see John, the postdoc, hand transpiled the circuits and I created pulses out of them. And we kind of did that together. And now we just have it implemented in Qiskit. So you can actually do that with just a few lines of code. I mean, I can show you in like one notebook what took us like 6 months to do. How do we host this? I think we're trying to iron out the details about how do we host this? How do we convey the information? I don't know if you've heard this other adage about physicists, but the answer is that physicists are the adage is physicists are not good coders. They just know enough to be dangerous.
Right.
and
yes, research code is not usually meant as a compliment.
Exactly. Your job is to be able to code enough to get your project done, to get your experiment done, to get your theory worked out, and to never be used again, to never be seen by anyone. That is a kind of stereotype that I think actually is pretty true. But at the same time, as someone who's switched from the hardware to the software side of things, there is so much about open source practices that I did not know. They do not teach physicists this. They do not teach physicists how to code in grad school. They do not teach you anything about how to do open sources, how to do pull requests, how to use continuous integration or talks and lint and all this stuff that I've only picked up in the past couple of years. Yet, because these tools really enable people to do more, to amplify their ability to show off their code or to use other people's codes for their ends, I think it's actually kind of misplaced. I think physicists probably should know how to do this. It shouldn't be coming to me later in life like this.
Almost as a necessary prerequisite in many domains towards getting to decent open science practices. I mean,
exactly.
Yeah, exactly. The same thing is happening in ML as well. I mean, they're trying to raise the standard, the expectation with respect to, you can't just like write a paper and give us the algorithm. They show us, working code and functional data sets. And in many other sciences as well, it feels like they're like sort of trying to drive as much as they can towards a demand to present all the data and show us your framework, rather than just publish a paper and see if we can figure out how to reproduce.
Right, and there's always, there was one kind of famous retraction that occurred in quantum physics recently, and since then there's been a huge push to try and do a better job of this. Publish your data, even in scientific experiments, publish the code that you wrote to analyze it. And I completely support this, and I think we just have to figure out how do we make this the most useful, because there's different repositories for doing this. There's kind of this archive thing is a preprint repository for throwing your results out there before they've been peer reviewed. Then they get peer reviewed in a journal that may or may not be open access. Maybe you have to have an institutional subscription for that journal. But this is exactly some of the things I've been talking about, Sebastian, is we should ask that people publish their code, and we can even maybe help them with that. I don't know. I don't know if we want to incur so much technical debt, but
it does feel like something that the quantum physics community as a whole would benefit from enormously. Like, and regardless of what university you're from, or what country you're from, or what company you're from, I think it would be good for everybody personally. Because it's funny, it sort of fits in with a larger trend, I think, that's happening in the physical sciences generally, which is they're becoming digital, right? I mean, the younger, sort of PhD or master's level students I encounter in chemistry and physics, they're using software tools as much as anybody else is, right? They think of software as being core to their discipline, and it's not whiteboards or chalkboards or just a lab table anymore. It always involves the cloud and open source software and all the rest of the tools that are familiar to everybody else from every other walk of life, really.
Just as I was saying, it amplifies your ability to do something. I don't want to fill pipettes all day for my biology experiments. No, I want to program a computer to do that for me.
I just want to circle back before we get too far from it, because you mentioned, so this is the work with University of Pittsburgh, David Pecker, and at the ground level, you were working on trying to decompose this large collection of CNOTs into ZX and pulse shaping or pulse amplification. But at the top level, you were saying that what you were trying to do is actually create Majorana braiding on superconducting qubits. Is that right?
Yeah, that is correct. So let me take a step back and talk about what that means, because this is, in general, something I'm interested.
I find that fascinating.
A fascinating topic, really is.
Yeah.
Okay, so one of the things I really love about condensed matter physics and why I studied it is because you can understand the properties of materials, even crazy materials like superconductors, with relatively simple models. So what do I mean? I mean, in your first elementary solid state physics class, you'll learn what is the by looking at the density of states of electrons and your band theory of solids, you can classify all your materials as an insulator, a metal, or a semiconductor, for example. And this is like what you learn how to do in your first semester, for example. And then if you want to see some more kind of exotic properties, what you do is you're like, well, I know everything's kind of obeys these band theory, or maybe it doesn't, if it's a really crazy thing, then sometimes things break down. But for a lot of phenomenon that are crazy inside of these materials actually come from some kind of model effect, which can be described like as some very simple interaction, which you can model as something I call maybe a model or a toy Hamiltonian. And Hamiltonians is how physicists understand all problems. It essentially describes the dynamics of your system, of your wave function, in terms of a Hamiltonian, which as its eigenvalues are the energy of the system. So it gives you how the time evolves as a function of the energies, which can be in a superposition and all the like. To boil it down, but a lot of interesting phenomenon, including superconductivity, for example, comes when you say, well, if I just change this Hamiltonian, or if I put this little model on top of it and have, like, say, what if electrons could be attracted to each other, because that's what happens in superconductors, then I can describe all of these properties from this very relatively simple or toy system. I could describe this massive thing with 10 to the 23 electrons in it or something like that. I mean, same with Majoranas, for example. You can write down the Hamiltonian that will give you P-wave spinless superconductivity. Now, getting something to realize spinless P-wave superconductivity is really hard, because most superconductors want to be S-wave or D-wave, and most electrons, by which I mean all electrons, have spin 1/2 and are not spinless. So creating Majoranas in the lab is something that's very, very difficult. And my condensed matter physics lab had some work in that. I was not related to actually building these kinds of things, but it was, in the lab, so I was somewhat familiar with it. But the basic idea is you can make the minimal, like the simplest model of Majorana braiding, and you can do it in these 3 nanowires. We call it a trijunction. And so he said, well, if we have the simplest thing possible, then we have like 3 sites or 3 modes we can do with 3 qubits, and we can do this kind of braiding algorithm where we change the couplings between them, and then we observe the Hamiltonian evolve, which is time dependent, and do the evolution of the system and to see what the braiding state is. And it turns out this is nothing you can't do with a pocket calculator, by the way, but you can demonstrate this on a quantum computer by being very smart, transforming your Hamiltonian into something that only has 2 body terms, and then doing some pulse scaling. You can achieve a result. Now, is this something that anyone didn't expect? No, we totally knew what was going to happen. Can we actually implement this on a quantum computer that has a real-life noise and real-life topology? Yes, it turns out if you're really smart, you can do that. Now, then what we want to look to is, people studying these toy models for, in the future, when you can start applying these to bigger systems, and you can start, you have a larger quantum computer in which you can study things that you can't model with your laptop or whatever, then you can actually start to learn something about these materials. And this is why I'm so excited about this, is because it really brings it back to what I studied in grad school. And these toy models are the kinds of things I learned in my solid state, advanced solid state physics class. So it's actually getting to experiment with that and helping other researchers in the field take those models and employ them on a quantum computer. That really makes me excited.
Yeah. I mean, it seems like we're right at the pattern you just described is small number of qubits, noisy qubits, toy problems, but we're right at the cusp of having larger numbers of qubits that are unsimulatable, right? That you can now implement these same approaches that you've learned on something as you said, you can replicate on a pocket calculator. I'm not sure everybody could do that, but we're getting devices now that you can take all that learning and start to implement it in a way that you could not do with classical means.
Exactly. And the idea is so what I'm doing is kind of the more textbook Hamiltonian evolution techniques, where I am assuming I can evolve all of these things, and I'm just going to let my system run until I run out of coherence. I'm swamped out by error. But there's other techniques such as variational algorithms, such as variational quantum eigensolver, quantum approximate optimization algorithm, et cetera, that we call more variational, which is where you can actually take a larger set of qubits and you don't need to run them as deeply, and then you can do measurements on them, so you don't have to rely on the coherence. And especially with limited topologies, those errors start to build up quite a bit in the larger systems. But what happens is you can do larger problems, and then you can figure out how do I bridge the gap between having a larger number of qubits with maybe a shorter number of operations and an algorithm that will do the kind of perfect time evolution, which you ideally would want to do. And how do I kind of trade those off and figure out different ways of doing that? And because these variational algorithms are kind of how do I say heuristic, I suppose is the right word. They involve ansatz, which is a fancy German word for guess, and they involve a lot of techniques that are, to be honest, still being developed by the week. We have a new paper that was put out by my colleague Bryce Fuller and Antonio Mezzacapo, where they looked at the classes of problems and different ways you could solve them, and found there's actually all these other classes too. It's a very, very interesting field, and
really dynamic, really interesting. No doubt. And so this is touching on really one of the most compelling topics I find within this domain, right? Where are we going to see in the short to medium term the big breakthroughs? I think many people who are new to quantum computing and hear a lot of the PR propaganda about it, they're focused on stuff like Shor's algorithm and outcomes that could be very, very far distant in the future. But more pragmatically, it feels like we're on the verge of seeing some big breakthroughs of significant outcomes, either on some of the experimental stuff that you just talked about in terms of using quantum computing frameworks to explore fundamental questions in physics, or some new breakthrough with respect to optimization algorithms, which of course physics has a long, prestigious heritage of making gigantic breakthroughs for other data scientists, right? So, what's your intuition? I know you can't predict the future, but do you feel like one of these two frontiers is going to see a big breakthrough soon? And if so, which one do you think it is?
Okay, so actually they have very, I'm starting to appreciate that they're actually very similar in a lot of ways, the optimization and the kind of materials Hamiltonians. The optimization gets mapped to a Hamiltonian at the end of the day, and the way you do, say, QAOA and VQE, it's not that different from each other. The thing that is different from each other, and the reason why I think the chemistry might have a better chance, is, at least naively, because I am a physicist, I understand the chemistry better than the optimization. But there are certain kinds of information that you can put inside of your ansatz that tells you something about the physical system. Because the physical system obeys this Hamiltonian, you can try to search your states and try and put that information inside of your guess states for your VQE algorithm. I'm sure there's a way you can do that in optimization. I just don't know what it is. It seems like that's a little bit more rich, because we know in the end that we can do full time evolution, which is what I've been doing. But we can use that time evolution, at least in some part, to kind of create an informed guess initially. So that's the one thing and maybe it's because I don't understand optimization as well. That's the kind of little advantage, which is why I say that the chemistry problems are probably going to be the first ones to be solved.
To break.
Yeah.
Interesting.
As someone who also doesn't do this for a living, I only do the toy Hamiltonians.
I would still classify yours as an informed guess, an informed
it's informed guess. I try to pay attention to the field, and know what people are doing. But people are making advances. There are so many good ideas out there, and this is what gets me excited about the software as well. The more people I can get to test ideas inside Qiskit, the better it is for everyone, because I can get if I make it easy for a professor to say, like, I think I have some ideas about how to break this problem down, and I can do it with your software without having to think too hard about it, then that just opens up more avenues for research.
Right. It's fascinating. And before I'm going to dip back into the work with Pekka, because I have one more question about the braiding.
Of course.
So you are, I mean, is it accurate to say you're trying to simulate a Majorana state using the qubits? And if so, like, would there be any learnings there or applications there that would help in terms of error mitigation or error correction? Because, I mean, obviously the topological qubits are sort of, this promised advantage. If you can realize a qubit using Majoranas, there's lower error rates because topological qubits are sort of self-correcting in some ways. Is there some sense that if you can simulate Majorana braiding on superconducting qubits, that somehow you're going to get some advantage in error correction or learn how to do error correction in a new way?
That is a great question, Sebastian. That is also something I've thought about. For our listeners, I don't know how many people know, but the kinds of quantum error correction that we plan to use on our superconducting quantum qubits is based on topological quantum computing and these things originally called torque codes because they existed on a donut or torus. Now we call them surface codes because it turns out you can just cut the donut up and turn it into a flat piece of paper or silicon, whatever. So there's this history of topology inspiring error correction essentially by looking at the topological, which means the non-local properties. It's like the property of the whole, like how many holes are in it, for example, versus like what's each qubit doing specifically. So one of the things that we had thought about is, well, what if you can do this braiding and that could inspire some sort of error correction protocol? Now, I'm not smart enough to know this, and I'm not because I'm not a theorist. Maybe I have an intern who is, so can ask her. But what happens is when you map the Majorana fermions into qubits, you have to do some sort of transformation. So there are common transformations. We do this because fermions obey called fermionic statistics. Bosons obey bosonic statistics, and qubits essentially are spins that obey the Pauli matrix statistics. So what happens is, in order for you to map the statistics of one onto the other to make the qubits behave like fermions, you have to kind of put them in a certain ordering so that you can get them to obey the same relations. They're commutators. But basically, this is a problem that people have known how to do for a very long time. And the oldest one is from the 1930s called the Jordan-Wigner transformation. And that's the transformation we used. It is qubit preserving, which means you have the same number of fermions as qubits. There are a lot of more recent developments in the field, such as the Bravik-Taev transformation. There's also the BK superfast. There's parity. There's a lot of work going on in this field, especially when you think about, well, there's no reason you need to go one-to-one fermion to qubit. That actually is not needed. You need some sort of logarithmic number in the number of fermions, depending on the problem. Like for my toy model Hamiltonians, everything's strongly interacting. So yeah, you probably need to do one-to-one. For molecules, where like this orbital over here doesn't talk to this orbital over here, you can probably get an advantage in mapping them smarter. So this is an area of constant research right now. And as far as what I understand is, under this mapping that we're doing, we're losing the topological nature of the Majoranas. But I can't tell you why, because I don't know. I don't know.
Hey, you're not saying it's a secret for your employer. You're saying you don't know.
No, I would love to know, and I would love to know if people had thought about this, because this came up, and I know we know that, or because I know this because I talked to my theorist collaborators. So I know that's true, but I don't know exactly, why it is. I'd have to probably play around with a whiteboard or something.
So this is a really great detail, and thank you. I maybe I have this wrong, but I had the impression, talking with other people who know Majorana fermions, that in a certain sense there's very strong theoretical justification for their existence, but there hasn't yet been to date, maybe I've got this wrong, but any experimental witnessing of these objects.
So that's a great controversial thing, but I will tell you what the facts are.
Let's hear it.
So the fact is, if you had a particle that obeyed the spinless p-wave superconducting Hamiltonian, you would have Majoranas. That is theoretically just proven, and that was done like more than 20 years ago, I think.
Yeah, a long time now. Yeah,
right. So you write down this equation, you say this does this, and then you're like, well, then I have a Majorana fermion, that everything's great. And that's true.
On paper.
Yeah, on paper. The problem is that's a spinless, and electrons have spin. It's a P wave, which is not a very common pairing in superconductivity. It's usually S wave or D wave, like I said. So what you have to do is you have to engineer a Hamiltonian by inducing effects or proximatizing your system in some weird ways. So this typically has to do with taking the best known example at this time is kind of taking a strong spin orbit coupling nanowire, a semiconducting nanowire, and inducing proximity in it by growing a really, really nice layer of a superconductor on top of it, an S-wave superconductor. So that'd be like aluminum. And you can induce these different states inside of it, and this was predicted to be kind of one of the ones that would host Majoranas. So where we're at right now is no one has proven the topological nature of any particle seen. People have signatures of what they think was Majoranas, but it's not conclusive. That's not the only system that you can do Majoranas with. You can also do topological insulators and topological superconductors and adding more magnetic stuff to it. It's all kinds of these interplay with these weird different states of matter. People think you can induce Majoranas into it, but it's a very, very difficult field because you need wildly different types of materials and you need really, really clean interfaces so that you can get this mixture.
Such a rich, chocolatey, crunchy topic, man. So thank you so much for delving deep.
You make a lot of friends at the party.
Well, for the right nerd scene, man, this is ideal. Yeah.
So, okay. So, in the spirit of wrapping up, is there anything you would want, given everything we talked about, anything we left out, anything you wanted to touch on that we haven't? Any last words?
So touch on. I think we got all around the kinds of things I was thinking about that I was hoping we could explore today. Last words, I suppose. I encourage people who are interested to get involved. There's many, not just Qiskit, but there's many open source software packages for exploring quantum computing and quantum phenomenon out there. And there's, not a week goes by where there's not another one. For example, I think I would encourage physicists to learn coding. I would encourage developers to learn physics and kind of cross those boundaries a little bit. And of course, there's so many other fields that are important for quantum computing. I don't want to just pretend it's computer science and physics. So I think it's a very diverse field. And, I would encourage anyone interested in it to kind of follow your passion because, whatever you're interested in, it probably has some intersection with, quantum computing. Say you're into, cryogenics or say lasers or say atomic physics or say microwave engineering.
All the cool stuff.
There's something there for you. Yeah.
You like hanging out in a clean room. That's cool too. You like shooting things with lasers. There's so many skills out there that are, can be very applicable to quantum computing. So I tell people to kind of follow whatever they're interested in and they'll find a way that intersects.
That's awesome. Thanks so much, Nick.
So fun. Nick, thanks a lot for your time, man. Really appreciate this.
Hey, thanks a lot for having me.
Wow, that was a great interview. I really enjoyed that. That was fun. What was so cool for me to hear from Nick was his sense of almost a clear-sighted realism on the short-term possible benefits of quantum computing. I mean, I think there's just an unhinged level of hype and a lack of contact, right, with the nuance of what trade-offs exist and what challenges are left to be overcome. But I mean, I do share his optimism. Right? Some of those chemistry applications, or maybe some of those new advanced physics experiments that you could do actually in code on QC,
right?
Hold immense short-term potential.
Right. Yeah, and the paper that Nick mentioned on variational techniques, we'll put a link in the show notes, which will be what we do with any kind of reference to research paper or other resources in future episodes as well.
Yeah, I mean, I think we've got some future podcast episodes that'll face that very question. So we take that variational algorithms as a
That's
topic
right.
pretty seriously. I mean, the other great thing was to hear Nick close with that inspiring invitation to bring more people into the quantum computing community. I mean, for a lot of hard science or math people that are really into this stuff, I mean, there really are some interesting frontiers out there in this domain. Even though it's a venture area where there is some economic risk, there's some cool careers ahead, it feels like.
Absolutely. I mean, I've always admired that about Nick, that he's one of the members of the community who are really passionate about the topic and about teaching the topic. He's always been very engaged with the educational pursuits, I would say, of quantum computing, which is terrific. At this early stage of the field, I think that's really important. As you said, there's a lot of really fascinating career paths. There's all kinds of incredibly exciting scientific breakthroughs and frontiers to be explored in this field, but we need to invite more people in, and Nick and people like Nick are really instrumental in expanding the community in that way.
We keep, I think, appropriately bringing up this theme of both our enthusiasm for the potential, but also mix that optimism with realism around the many challenging breakthroughs still left to be done before the full promise of this technology is fully realized. I mean, this particular mix of both that possibility alongside the huge market timing risks for investors. I mean, some of these enterprises, to me, they're just gigantic bets, and they're hanging on a knife's edge.
That's right. Yeah, and that's what we're going to try to do with future interviews. We'll try to get a mix of guests who can help us understand the foundations of the field. It's not that old a field. It's still very much, emerging out of physics and mathematics and complexity theory and other scientific domains and engineering domains. And so we'll talk to some pioneers or people who know the history really well as people who are now sort of driving the commercial development of the technologies and exploring some of the applications. As you said, I think we'll get into some really interesting conversations around commercial applications, but also scientific applications. Even at this stage, these machines may have shortcomings as computers, but they are really exotic and powerful lab instruments.
Yeah, producing results right now. Absolutely.
Exactly. I know a lot of scientists are starting to explore what kinds of discoveries in physics that can be derived just from the systems that we have today. So lots and lots of exciting stuff coming up. Really hoping that our audience is going to appreciate that, and we'll be adding ways around the show and the site to provide feedback and engage with the audience to get people's opinions and see what we can do to improve the show over time.
Good stuff. Yeah, interesting time to be alive.
Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian and Kevin Roney. Our cool theme music was composed and played by Omar Hamido. Production work is done by our wonderful team over at Podfly. If you are at all like us and enjoy this rich, deep, and complex topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you heard, reviewing us on iTunes and/or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic. We would really appreciate your help spreading the word and building community. Thank you so much for your time.